Hello and welcome back to our final lecture, our last one in the statistics lecture series for ENIGMA-U. We just talked about what correlation is, how to use it, and what sorts of things it can show us in terms of our scientific results. And now we're going to talk about some of the ways that we can use correlation, what we should use it for, and what we should absolutely not be using it for. So the situations, in which we should use correlation are threefold. The first is in prediction and theory verification. So a lot of psychological and scientific theories are going to make predictions about the relationship between two variables, and we can use correlation to test, to test if those predictions and theories are correct by correlating them. The second use of correlation is a measure of reliability. So a measurement procedure is going to be considered reliable to the extent that it produces stable and consistent measurements. So we can use correlation to figure that out. And validity. And a measurement procedure is considered valid to the extent that it measures what is intended to measure. And correlation does both of those things. So here are some ways that we can interpret correlation and some errors that people often make when they try to interpret correlation. We're going to talk about each of these four things in depth over the next several slides, but the first and arguably most important thing we're going to talk about is that correlation does not equal causation. Although there might be a causal relationship, just the existence of correlation alone does not prove it, and we cannot interpret correlation as such. The second is to make sure that there is not a restricted range in your data, because the value of a correlation can be greatly affected by the range of scores that you use. The third is to be extremely careful about outliers, because one or two extreme data points in your set can have a huge effect on the value of a correlation coefficient. And the fourth and final thing we're going to talk about is that correlation does not equal proportion. So a correlation of 1 means there's a perfect one-to-one relationship. A correlation of 0.5 doesn't mean that you can make predictions with 50% accuracy. And we'll talk about each of these four things on the next several slides. The first is that correlation does not equal causation. This is one of the most common errors in interpreting correlation, assuming that a correlation implies that there's a cause and effect relationship between those two variables, which is not the case. Correlation determines whether or not a relationship exists between two variables. It does not determine, or basically, when X moves, does Y move as well? And if so, how? It does not determine causation, which would say Y moves because X moved. It's not the same thing, and we can't use correlation to determine causation. If we wanted to establish a cause and effect relationship, we could, but we would need to make sure that the three criteria of causation are met. First is covariance, that variable X varies along with variable Y, and covariance is one of the things we measure with correlation. However, correlation does not measure these second two. Temporal precedence, which means that the change in one variable occurs before the change in the other variable, which is necessary if there's a cause and effect relationship, right? One of the variables has to change, and then that makes the other variable change. And then the third is internal validity. So we need to make sure that there's not some other confounding variable that is causing the changes in X and Y that we just haven't figured out. And in order to establish internal validity, we need to conduct a true experiment. So we need to hold all of our other variables constant while one variable is manipulated. And that is not something that we do in a correlation hypothesis test. I thought this little thing was cute. This little comic, it says, I used to think that correlation implied causation. Then I just took a statistic class and now I don't. Sounds like the class helped. Well, maybe, because he's saying just because it correlated does not mean that the statistics class caused it. Funny. Last thing we'll say too is that correlations can often provide clues to causation, but they don't demonstrate or test for causality. These further tests are necessary to determine a cause and effect relationship. There are two problems that we do not address when we're just testing for correlation, and those are the directionality problem, where correlation can't establish temporal precedence, and the third variable problem, correlation can't establish internal validity, these two other variables. Let's look at this with an example. So say that we're looking at the correlation between two variables. Let's say that it's absences during the school year and final grades. We could hypothesize that fewer absences cause higher final grades. There's a negative correlation there. And maybe that is the case, that fewer absences cause higher final grades, but it's unlikely, but possible that the reverse is true. Maybe getting higher final grades causes you to have fewer absences. But what's more likely is that there's a possibility of a third confounding variable. Maybe in that situation, the confounding variable is actually internal motivation levels. Maybe students with higher internal motivation levels have fewer absences and higher final grades. But since we didn't perform a true experiment, we can't count that out, right? So in these are the two problems with using correlation to determine causation. I just thought this was interesting. Here are three separate examples where correlation was found, but it would be ridiculous to assume that there was a cause and effect relationship. The first is that marriage rates, let's look at marriage rates in Utah based on the US Census, and per capita consumption of high fructose corn syrup. There is a very strong positive correlation, and it is significant, but we cannot say that marriage rates increased, that the increase in marriage rates caused more people to eat high fructose corn syrup. That's ridiculous. A second is the number of films that Nicolas Cage appeared in and the number of males in Washington who slipped or tripped to their death between 1999 and 2009. There is a moderate correlation that is pretty significant, but we're not going to say that as Nicolas Cage performed in more movies, it caused more people in Washington to slip to their death. That's not cause and effect. And the last is Apple iPhone sales and the number of people who died from falling off a cliff. There is an almost perfect correlation, but that does not mean that there's any cause and effect. Okay. The next way that we can interpret correlation is we have to be careful about whether or not there is a restricted range. So for a correlation to provide accurate description for a general population, there should be a very wide range of X and Y values. We have what is called a restricted range when we have scores that don't represent the full range of possible values. And when we have a restricted range, we can't generalize our correlation beyond the sample of data that we have. We can't generalize it to the main population. Because sometimes, as we can see here, we have the full data set here, and we find that there's an R of 0.5, which is a moderate positive correlation. However, when we just take a restricted range from the ages of 22 to 25, we see that now our R value drops all the way down to 0.05, which is there's almost no relationship there. So sometimes taking a range can hide that there's actually a correlation there. The opposite could also be true. Sometimes you can have a subset of your data, a restricted range, that makes it look like there is a correlation, but then when you widen your lens and use the whole data set, you can see that there was actually no correlation or less of a correlation to begin with. So it's always better to have more data. And just remember that when you're performing your research studies, that if you have a restricted range, you cannot generalize your correlation results. The third thing we're going to talk about is looking for outliers in your correlation data. An outlier is an individual with either X or Y values or both that are substantially different, either much bigger or much smaller than the values that were obtained for the other individuals in your data set. It generally looks like this. We can see that this point has a much higher X and a much higher Y value than the rest of these data points. And so that's another reason why it's so important to examine our scatter plots for outlier or before we calculate a correlation coefficient. We also need to be looking for outliers in our scatter plots, because what you can see here is when we say, what this says here is one student who both studies and uses her cell phone, here, hours studied per week, monthly cell phone bill, more than any other individual in the sample, changed the coefficient from negative 0.14 with just these guys, which was a weak negative correlation, all the way up to 0.39, which is a moderate positive correlation, if you include just this data point. So sometimes you can take outliers out if you realize that it was a data collection error that led to your outliers. For example, if I don't know, if someone was administering a psychological test and it turned out they administered it incorrectly, and so you got an outlier, you could take that out, but it's always important to report it if you do that. Report it in your paper. More often than not, you just mention that there is an outlier in your data. The last thing we're going to talk about is the idea that correlation does not equal proportion. So just because two variables correlate with each other, that doesn't mean that we can use one of them to estimate what the other one is going to be. That's what proportion means. So in order to describe how accurately one variable does predict another, in order to accurately describe proportion, we actually just take our correlation coefficient and we square it. Instead of using R, we're going to use R squared. It's called the coefficient of determination. And it is just what we said. It's a measure of the proportion of variability in one variable that can be determined from the relationship with another variable. Let's look at some examples here. So this first one says, in this case, the correlation R is 0 and R squared is also 0. What that means is there's no correlation between shoe size and IQ, and by extension, any knowledge that you have about shoe size does not allow you to predict anything about the IQ of another person. Or in other words, the variability in shoe size is accounted for 0% by the variability in IQ. These data in the middle show a moderate positive correlation of 0.6, but their coefficient of determination is 0.36. What that tells us is that folks with high IQs tend to also have high college GPAs, but it's not a perfect correlation and it's not a perfect proportion either. In other words, knowing information about someone's IQ can probably tell you a little bit about their college GPA, but you can't be sure of it. In other words, it means that 36% of the variation in GPA can be explained by IQ. So it's not a lot, but it's 36%, so it's not nothing. In this last example here, we show a perfect linear relationship of 1, which means that our coefficient of determination is also 1. This between annual salary and monthly salary. So what that means is if you know a person's annual salary, you can predict the person's monthly salary with perfect accuracy and vice versa. In other words, if two people have completely different annual salaries, the difference can be completely explained 100% by the difference in their monthly salaries as well. So correlation does not tell you about proportion. It can't allow you to predict, but it can give you information. You can create the coefficient of determination, which will allow you some information about that. Okay, just like with every other form of hypothesis testing we've talked about, it is also important to report effect size when you're using correlation. And the good news about effect size is that it's built into our correlation coefficient. As we talked about before, our correlation coefficient of R tells us the direction, form, and strength of the relationship between two variables. So we actually just use R by itself, and that's enough to tell us about the nature of the relationship and the strength of the relationship. Here are the R effect size conventions. A correlation of positive or negative 0.1 is weak, positive or negative 0.3 is considered moderate, and positive or negative 0.5 is considered a strong correlation. And the next way that we can report effect size is we can also use the coefficient of determination, which we just talked about, R squared, to talk about the strength of a relationship. This, instead of just telling us the strength of the correlation, tells us the proportion of variance in one variable that is accounted for by its relationship with the other variable. So an effect size of R squared of 0.01 is considered small, 0.09 is medium, and 0.25 is large. And lastly, these are some other types of correlation coefficients that we can use in statistics to evaluate correlations between relationships. when our variables are less than continuous. So Pearson's R can only be used if both variables are continuous. But if we have one variable that's ordinal, or if we have two variables that are ordinal, we use something called Spearman's rho. We can also use a point biserial R, a biserial R, or a phi coefficient as well. Phi coefficient as well. We're not going to talk about these right now, but if you're interested, I would encourage you to do some research on your own, learn about the context in which you would use these things. From these lectures, you definitely have the building blocks of statistics to be able to understand these coefficients, and it's an awesome next step in expanding your statistical knowledge. And with that, we have reached the end of our statistics course in ENIGMA-U. Thank you so much for joining me through this lecture series, and I hope that you feel more confident about statistical analyses at this point in your life, and you feel like you can use them to help design your own research studies and make your own science a little more robust and reliable. I hope that next time you read a scientific paper, you won't just skip over the statistical part in the method section, but that you'll read it and then you'll use your statistical knowledge to evaluate the rigor and reliability of the research that you come in contact with. Yeah, I wish you all of the luck in your everything that you are trying to do for the rest of your life. And with that, I'm going to sign off.